Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine, just for a second, standing at the absolute edge of existence.
Well, that is a pretty terrifying place to start.
Right. But just humor me here. You are hovering just millimeters away from a boundary that is so profound and, so final that right before everything goes dark forever, the universe itself actually rings like a bell.
A cosmic bell, yeah.
Exactly, because it's basically a fundamental law of physics and, well, a massive pop culture cliche at this point, that in the vacuum of space, no one can hear you scream.
Because there's no air?
Right. There's no medium for acoustic sound to travel through. Space is just this silent void. But there's this massive paradox sitting right at the center of modern astrophysics right now.
Oh, absolutely.
We actually know that there is a way to, quote-unquote, hear the violent cataclysmic crash of two black holes colliding.
Which is such a profound contradiction when you really think about it. I mean, we're talking about the darkest, most invisible objects in the universe.
Yeah.
And they are creating the most energetic outburst of noise imaginable. But not a sound moving through the air, of course.
Right.
It's a sound moving through the very geometry of reality.
Okay, so let's unpack this, because what we are embarking on today is basically a journey to decode the loudest gravitational wave ever recorded by human beings.
It really is a milestone.
It is. Our mission here is to transport you, the listener, right to the edge of an event horizon during a cosmic collision. And we're going to explore what this totally unprecedented signal tells us about, well, the most impenetrable boundary in the entire cosmos.
And we really should establish right away that we aren't just talking about a loud noise in some abstract or, theoretical sense.
Right.
When a signal of this magnitude hits our detectors, we're essentially unlocking spacetime's deepest secrets. We're peeling back the layers of physics that govern how the universe operates at its absolute extreme limits.
The places where things get weird.
Exactly. The places where our standard equations actually start to break down.
So to really grasp the gravity of this, and yes, that pun is fully intended.
Nice.
Thank you. We have to look at the signal that started it all. This was basically a cosmic alarm bell ringing across the universe. The event is centered around a signal designated as GW 2501115.
Recorded just last year, right? In 2025.
Yep, 2025. By the two laser interferometer gravitational wave observatories, or, LIGO, as most people know it, here in the United States. And the major headline here is that it is the loudest binary black hole signal observed to date.
Which is staggering.
It really is. I mean, we are talking roughly 3 times louder than the very first gravitational wave ever detected just a decade ago.
In the concept of loudness in gravitational wave astronomy, it kind of requires us to completely discard our biological experience of hearing.
Because there are no sound waves.
Right. When astrophysicists say loud, they're actually referring to amplitude.
Amplitude, okay.
Yeah. Gravitational waves are physical ripples in the actual fabric of space-time. And you always hear people compare space-time to a flat trampoline, which is...
the bowling ball on the trampoline analogy.
Yes. And it is a terrible, overused analogy that completely fails to capture the three-dimensional nature of the universe.
So what's a better way to picture it?
Think of space-time, instead, as a massive solid block of dense, clear gelatin.
Okay, a giant block of cosmic jello. I can work with that.
A giant block of cosmic jello, exactly. So if you take 2 dense, heavy marbles and embed them deep inside that gelatin,
right,
and then you start spinning them around each other at a significant fraction of the speed of light, they're going to violently churn that material.
Oh, I see.
And when they finally smash together, that massive collision sends these severe pressure waves rippling outward through the gelatin in all 3 dimensions at once.
Okay, so when those ripples finally reach Earth, after traveling outward for, maybe billions of years, they are actually physically stretching and squeezing the space that we occupy.
That's exactly what's happening.
So, think about where you are sitting right now listening to this. As this specific wave passed through Earth, the room you're in, the chair you're sitting on, and literally your own body were physically stretched and squeezed, oscillating back and forth.
You were, but we do need to emphasize that this is on a microscopic scale.
Right. Nobody actually felt it.
No. We are talking about distortions that alter the distance between here and the nearest star by roughly the width of a human hair.
That's almost impossible to even conceptualize.
Or to bring it locally, it's like changing the length of LIGO's 4-kilometer-long vacuum tubes by just a fraction of the width of a single proton.
Which honestly makes the engineering behind LIGO sound completely impossible. We aren't just talking about building a really big telescope here.
Not at all.
These facilities, they're in Washington State and Louisiana, right?
Yes, those are the two.
They are shooting lasers down these 4-kilometer-long vacuum tubes, bouncing them off perfectly suspended mirrors, and basically measuring how long it takes for the light to return.
And the precision required to pull that off is just difficult to overstate. To measure a distortion smaller than a proton, you have to isolate those mirrors from the seismic noise of the Earth itself.
Right, because everything vibrates.
Everything. A truck driving down a highway miles away, or a wave crashing on some distant shoreline. Even the microscopic thermal vibrations of the actual atoms inside the mirrors themselves.
Wait, really? The heat of the atoms in the mirror can mess up the reading?
Oh, absolutely. All of that creates background noise.
Yeah.
So LIGO has to mathematically and physically cancel out the ambient vibration of the entire planet just to hear the universe whisper.
That is just wild. And, that rapid progression of our technological ability over just the last 10 years is mind-blowing to me.
It's been incredibly fast.
Like a decade ago, just confirming that these ripples existed at all was this monumental Nobel Prize-winning triumph. And now, just 10 years later, we capture a signal 3 times as powerful, and we're using it as this incredibly precise surgical instrument to probe the black holes themselves.
Well, and the amplitude is what allows for that surgical precision.
Because it's louder.
Right. A louder signal means that the stretching and squeezing of space-time was significantly more pronounced. It implies immense energy, and crucially, it implies proximity.
Proximity. So GW 25011 was close to us.
Relatively speaking, on a cosmic scale, yes. It happened relatively close to us.
Okay, let me throw out an analogy here to see if I'm visualizing the impact of this amplitude correctly.
Sure, let's hear it.
So if the first gravitational wave we detected a decade ago was kind of like feeling the faint rhythmic rumble of a distant train through the soles of your shoes while you're standing, 5 miles away.
Okay.
Is GW 25011 Tor more like standing right next to the tracks as a massive freight train blasts its horn and just rattles your ribcage?
I like that, but let's actually take that train analogy a step further.
Okay.
When you're 5 miles away, you really only feel the lowest, deepest bass frequencies of that rumble, right?
Yeah, just the heavy vibrations.
Exactly. The higher, more delicate frequencies, like the metal wheels clacking on the rails, those are completely lost to the intervening distance and the soil.
That makes sense.
But by standing right next to the tracks, you don't just feel a stronger rumble. Your ear can suddenly pick up the complex, subtle harmonics of the machinery itself.
Oh, I see. So the volume doesn't just make the main event easier to notice.
No.
The high volume actually allows us to hear entirely different layers of the collision.
It unveils the harmonics. It's like in music, A piano key doesn't just produce one pure mathematical tone when you strike it.
Right.
It produces a fundamental frequency, but alongside dozens of overtones. These are higher, quieter frequencies resonating simultaneously.
And that's what makes it sound like a piano and not a computer beep.
Precisely. Those overtones give the instrument its character. So in gravitational waves, the main roar is the bulk of the collision.
The huge smash.
But a profoundly loud signal, like GW 25011 has such an incredibly high signal-to-noise ratio that the faint overtones of the collision finally rise above the background static of the universe.
Wow. Which brings just a completely new layer of data to the table. We aren't just hearing the smash anymore. We're actually hearing the subtle vibrations of the new black hole settling down.
Yes, the ring down.
And that shifts our focus directly to the true protagonist of this whole cosmic drama, which is the event horizon.
The point of no return.
Exactly. This is the universe's ultimate point of no return. We know the basics, right? It's the boundary around a black hole where absolutely nothing, not even light, can escape. But for anyone familiar with the basic physics of gravity, the mechanics of this boundary get incredibly strange.
Oh, very strange. And the strangeness really comes from the absolute finality of the universal speed limit.
The speed of light.
Right. We know that as mass increases, the escape velocity, which is the speed required to break free of an object's gravitational pull, that increases too.
Like how it's harder to launch a rocket from Jupiter than from Earth.
Exactly. And at a certain point of mass density, that required escape velocity hits exactly 299,792 kilometers per second.
Which is the speed of light in a vacuum.
Yes.
And since Einstein's equations dictate that nothing can travel faster than the speed of light, anything that crosses that mathematical boundary is just permanently trapped.
It is a one-way door in the universe. Information, matter, light. It goes in and it never comes out.
Which presents a pretty profound paradox for observational astronomy, doesn't it?
A huge one.
Because how do you observe an object that, by its very definition, completely forbids observation? If no light, no radiation, and literally no information can cross from the inside of the event horizon to the outside universe, you're essentially trying to study a shadow by, turning off all the lights.
Yeah, that paradox is really what trips up a lot of people when they first look at the data from GW250112.
I know, it tripped me up. I was like, if it's the ultimate trap, how did scientists witness it? We literally can't see the black hole itself.
Well, the key is that we aren't seeing what comes out of it because nothing does. Okay. Instead, we are witnessing the severe, agonizing warping of the space-time directly adjacent to the horizon in the exact millisecond it is forming.
Oh, so it's the space around it.
Yes. When two black holes merge, their individual event horizons deform. They stretch toward each other, and they finally fuse to form a single, larger, and highly chaotic event horizon.
Highly chaotic. So for a fraction of a second, this newly born remnant black hole is not a perfect sphere.
Far from it. It is violently asymmetrical.
Really?
Oh yeah, it is wobbling, ringing, and shedding immense amounts of energy in the form of gravitational waves as it desperately attempts to settle down into a stable spherical state.
Wow.
It's that dynamic, turbulent boundary, the space-time actively reacting to the violent birth of the horizon that we are observing. We're essentially catching the shadow just before the door slams shut forever.
That is such a cool way to phrase it, catching the shadow before the door slams shut. And the method scientists use to actually capture that fleeting moment before the eternal dark is just a brilliant piece of analytical detective work.
It really is.
This research was led by Dr. Ling's son and PhD candidate Neil Liu. They're over at Osgrav and the Australian National University, right?
Yes, working with an international coalition spanning Canada, the U.S., and Spain.
Just a massive global effort. And they managed to basically isolate the last sound these black holes made.
And the secret to measuring this last sound lies in a very specific, notoriously elusive component of this signal called direct waves.
Direct waves.
Okay, yeah. Prior to this analysis, direct waves were theoretically understood, but practically impossible to extract from the noise.
They were just buried.
Exactly. But Neil Liu's new analytical framework essentially deciphered them. It pulled completely unique data from incredibly close to the event horizon.
Okay, so let's dig into the how of that extraction, because they couldn't just use a standard audio filter to clean up the track. I was looking into the computational mechanics behind this, and the process of mathematical dissection is just staggering.
It's intense.
They had to rely heavily on something called numerical relativity, right?
Yeah, they did. And numerical relativity is basically the unsung hero of gravitational wave astronomy.
How so?
Well, Einstein's equations of general relativity, they are nonlinear partial differential equations.
Which means they're a nightmare to solve.
They are famously brutally difficult to solve. For decades, physicists could really only solve them for highly simplified, idealized scenarios. You cannot just write down the exact solution for two black holes merging on a chalkboard.
You need a supercomputer.
You need massive clusters of supercomputers running for months just to simulate a fraction of a second of a black hole merger.
Months for a fraction of a second.
Yes. The research team had to model millions of potential merger scenarios. They simulate the exact masses, the spins, and the orbital trajectories of the two black holes. And then the computers crunch Einstein's equations to predict exactly what the main gravitational wave, that dominant roar, should look like.
Okay, so if the main crash, the bulk collision, is a deafening orchestral cymbal smash happening right in front of you, these direct waves are like a tiny specific vibration of one single violin string happening at the exact same millisecond.
That's a great way to picture it.
So to find the violin string, they use the supercomputer to map out the exact acoustic profile of the cymbal smash.
Right.
And then they mathematically subtract it from the raw LIGO data.
That's exactly what they do. But that subtraction requires an unprecedented level of precision.
I can imagine.
If your numerical relativity model is off by even a fraction of a percent, the leftover data will just be statistical garbage.
Oh, because you didn't subtract the right thing.
Right. But by meticulously modeling and subtracting the dominant signal, which is the in-spiral and the immediate merger. What they were left with was a tiny residual vibration, the ring-down phase.
The violin string.
The direct waves. And the origin of those direct waves is really what makes them so invaluable to us.
Why is that? Where do they come from?
They don't come from the distant orbiting phase of the black holes. They are emitted right at the throat of the beast.
Wow.
They carry the untainted fingerprint of the extreme gravity immediately adjacent to the newly formed event horizon.
It's kind of like standing at a massive party with 100 conversations happening, heavy music playing, glasses clinking, and you're trying to hear a specific whisper from across the room.
Exactly.
Except here, the team is filtering out the noise of the universe itself to hear a single whisper from billions of light years away.
And the effort to isolate that single voice is driven by the totally unique physical environment it originates from.
The event horizon itself?
Yes. Black holes are the ultimate extreme laboratories. They sit precisely at the intersection of our two most successful, yet fundamentally incompatible, frameworks of physics.
Oh, right. General relativity and quantum theory.
Exactly.
This is where the physics gets incredibly tense.
Wow.
Because we have these two rule books, right? General relativity is the master theory of the massive. It explains gravity, orbits, and the smooth, continuous fabric of space and time.
Correct.
But then we have quantum mechanics, which is the master theory of the microscopic. It explains atoms, subatomic particles, and it treats the universe as chunky, like it's made of discrete packets of energy.
And under normal circumstances in the universe, those two rule books never have to speak to each other.
Right, because things are either huge or tiny.
Exactly. You use relativity for stars, and you use quantum mechanics for electrons. But at the event horizon of a black hole, the mass is so immense and the space it occupies is so compact that the gravity violently warps space-time on a microscopic quantum level.
It forces them together.
It is the singular place in the cosmos where the rules of the massive crash headlong into the rules of the microscopic.
So, okay, if these two frameworks fundamentally disagree on how the universe works, what does it actually mean for Dr. Sun and Neil Liu to use these direct waves to test general relativity?
Well, it's a huge deal.
Are we essentially using this super loud gravitational wave to see if Einstein's equations finally break down? Like, are we trying to prove him wrong?
Well, consider the implications of a breakdown. I mean, every single time physicists have tested general relativity over the last century, from the bending of starlight around the sun to the time dilation in GPS satellites.
He's always right.
Einstein has been proven flawlessly correct every time. But theorists know the theory is incomplete.
Because it produces infinities, right?
Right. At the very center of a black hole, the singularity, relativity, predicts infinite density and infinite curvature.
Which doesn't make sense.
No, because nature abhors an infinity. And an infinity usually just means your math stopped working.
Yeah.
So theorists suspect that right at the boundary, right at the event horizon, general relativity might begin to fray, revealing subtle quantum effects.
Oh, I see.
By isolating these direct waves, these little whispers from the absolute edge, the team is gathering the raw data needed to run the ultimate stress test. They are checking if Einstein's rulebook actually holds up under the most extreme pressure the universe can generate.
Man, that is fascinating. So to run those stress tests, the team had to pull incredibly specific measurements from that leftover whisper.
Very specific.
They had to essentially take the vitals of the newly born black hole. And the analysis of GW250114 allowed them to measure two fundamental properties of the remnant: its rotation frequency and its surface gravity.
And those two properties basically define the entire existence of the remnant.
And the remnant, just to be clear, is the single black hole left behind after the chaotic fusion.
Yes. And in that fusion process, a substantial percentage of the two parent black holes' combined mass is converted instantaneously into pure energy.
Oh, and that energy is the gravitational waves LIGO detected.
Exactly. E equals mc squared in its most violent form.
The mass just turns into a ripple in space.
Right. And what remains after that burst is a new entity. And when we measure its rotation frequency, we are measuring its spin.
Because they spin.
Black holes are rarely static, stationary objects. I mean, almost everything in the universe possesses angular momentum. Stars spin, galaxies spin.
Yeah.
When two massive black holes orbit each other and merge, all that tremendous orbital energy has to go somewhere. The law of conservation of angular momentum dictates that the rotational energy is inherited by the remnant.
Meaning the resulting black hole can be spinning at, like, a significant fraction of the speed of light.
Oh, absolutely. Speeds we can barely comprehend. And the second vital sign they measured, the surface gravity, That requires a bit of a conceptual adjustment.
Why is that?
Because, as we established earlier, a black hole doesn't have a physical solid surface.
Right. You can't land a rover on it. It's just a boundary.
Exactly. The term surface gravity is really borrowed from planetary physics. For a black hole, surface gravity refers to the strength of the gravitational pull precisely at the mathematical boundary of the event horizon.
Just right at the edge.
Right. It is a measure of how sharply, how steeply space-time is curved exactly at the point of no return.
You know, the mathematical reality here is actually stranger than fiction.
It usually is.
I mean, think about it. We are taking the vitals, the spin, and the gravity of a completely invisible light-trapping void sitting billions of light years away purely by mathematically dissecting the invisible ripples it cast off during its birth.
It is poetry. And those two properties give us a complete picture because of a concept known as the no-hair theorem.
The no-hair theorem.
Yes, it postulates that from the outside, an astrophysical black hole is incredibly simple. It has no complex identifying features, no hair.
Oh, I get it.
If you know its mass and its spin, you know absolutely everything there is to know about its macroscopic state. It is fully identified.
Okay, let's do it. So the basic definition is that a spinning black hole literally drags the fabric of space-time nearby along with it, creating an environment where absolutely nothing can remain stationary relative to a distant observer.
That's the definition, yeah.
But to actually visualize that, I think we have to go back to our gelatin analogy.
Definitely. We intuitively think of space as a static, rigid stage where events happen, like a three-dimensional grid, right?
Yeah, an empty room.
But Einstein taught us that space-time is a dynamic, tangible medium. So if you place a perfectly smooth, massive, stationary ball in our block of clear gelatin, it just sits there. It displaces the material around it, but that's it. That is standard gravity.
But if you start spinning that ball,
the friction of the ball's surface grips the gelatin. It doesn't just sit still anymore. The gelatin begins to swirl in a vortex around the spinning object.
Like twisting a spoon in a bowl of honey.
Yes. The material closest to the ball is dragged the fastest, and the effect tapers off the further away you get.
But wait, again, a black hole doesn't have a physical surface to create friction.
And the beauty of general relativity is that it doesn't need one.
It doesn't.
No. The mass itself, just by twisting through the geometry of the universe, drags the coordinate system of space along with it.
The coordinate system itself.
Yes. The swirling vortex of space-time around a spinning mass is the lens-thurring effect, or frame dragging. The mathematical reference frame of space itself is literally being pulled into a whirlpool.
Okay, let me push this to its logical extreme to make sure I am truly grasping the physics here, because this is wild.
Go for it.
Say I have an indestructible spaceship. I have infinite fuel and infinite thruster power.
Okay, a magical spaceship.
Right, and I fly right up to this newly born, rapidly spinning black hole, and I cross into the region just outside the event horizon, which is an area called the ergosphere, right?
Yes, the ergosphere.
So I get there, and I fire my thrusters perfectly to hover in one exact mathematical coordinate. I am trying to stand completely still.
Okay.
Do I stay still?
If you do that, you are fighting a losing battle against the geometry of the universe.
Really? Even with infinite power?
Even with infinite power. Inside the ergosphere, the frame dragging effect is so severe that space-time itself is being dragged around the black hole faster than the speed of light.
Wait. Nothing can move faster than light? That is the fundamental rule we just established for the event horizon.
Nothing can move through space faster than light. But space itself has no speed limit.
Really?
Think about the expansion of the universe. The universe itself expands faster than light.
Right. Okay.
So in the ergosphere, the local space is swirling so violently that to remain stationary, relative to me, like if I'm an observer back on Earth watching your spaceship through a telescope,
yeah,
to stay still relative to me, you would have to travel through your local space faster than light just to hold your ground.
Which is physically impossible.
Exactly impossible. Therefore, even with your infinite fuel and your infinite thruster power, you are inevitably swept along in the cosmic whirlpool. To you, inside the cockpit of the spaceship, you might feel like you are pushing as hard as you can in one direction. You are burning fuel at maximum capacity. But to me, looking at you from Earth, Your spaceship is being irresistibly swept sideways in a cosmic hurricane.
So you literally cannot stand still.
You cannot stand still because the stillness of space no longer exists there.
Think about the absolute wildness of that concept. The very fabric of where you are is moving. It sounds like pure, unfiltered science fiction.
It really does.
But this is a measurable, mathematically proven reality happening in our universe right now. And the true triumph of the research led by Dr. Sun and Neil Liu is that their analytical technique actually allows us to isolate the specific signatures of this frame, dragging from those tiny direct waves.
Yes, we are transitioning from merely cataloging the existence of black holes to actually charting the fluid dynamics of an invisible universe. We are mapping the whirlpools of space-time with excruciating precision.
It is truly staggering. So let's trace the arc of what we've explored today.
It's been a journey.
We started with the sheer violence of GW 250-114, a cosmic crash so massive it sent the loudest ripples ever recorded through the gelatin of spacetime. And we looked at how an international team of scientists used supercomputers and numerical relativity to mathematically subtract the deafening noise of that crash.
Which revealed the tiny, hidden direct waves.
Right, and those faint, lingering vibrations allowed us to bypass the paradox of the event horizon. We used those whispers to measure the spin and surface gravity of a newborn remnant.
Taking the vitals of an invisible ghost.
Exactly. And in doing so, we uncovered the reality of frame dragging, where the sheer rotational force of a black hole twists space-time itself into a cosmic treadmill where nothing can ever stand still.
It's beautiful.
It really highlights the absolute beauty of human ingenuity. I mean, we are sitting here on a pale blue dot orbiting a totally average star, yet with our minds, our supercomputers, and, lasers shooting down 4-kilometer vacuum tubes.
Can't forget the vacuum tubes.
Right. We can mathematically dissect the most extreme, bizarre environments in reality.
It is a remarkable perspective. The universe is incredibly vast and violently chaotic, yet it remains profoundly intelligible.
It follows rules.
It follows rules.
Yeah.
And piece by piece, frequency by frequency, we are learning to read the rule book.
Which leaves me with one final provocative thought for you to consider. We have established today that the event horizon is the ultimate eraser of information.
The ultimate trap.
It permanently swallows all light, sound, and matter. Once something crosses that boundary, it is gone from the observable universe forever.
Right.
Yet, right before that eraser activates, right in the millisecond before the door slams shut for eternity, the violent collision broadcasts its most intimate secrets. Its mass, its spin, its gravity across the cosmos via these gravitational direct waves.
It's quite a send-off.
The universe essentially screams its identity precisely at the moment of its erasure. Is this the universe's built-in mechanism for ensuring that nothing is ever truly erased without leaving a trace? If the universe rings like a bell right before it goes dark, what other invisible boundaries are out there right now just waiting for us to figure out how to listen?
It is a beautiful contradiction to end on. The darkness announces its arrival with absolute clarity.
It truly does. Keep looking up and keep listening.
Until next time.